Up next is Johnnie Driver doing the reporter for Group 2, Experiment 3.
So I'm doing Experiment 3, the Rankine cycle. And if you remember from thermo, the Rankine cycle is like the first cycle you really learn. It goes, and there's a constant pressure line, and there's a constant pressure line. So you have state 1, 2, 3, 4, and 5. If this is a T, V diagram, where these are constant pressure lines, basically what we were doing in this lab is testing this Rankine cycle to show that if you do the actual calculations on a real experiment, it should get somewhere close to the ideal cycle, even though you know you're not going to get exactly close because of resistance and things like that. So the theory behind it, water is pumped into the closed container called a boiler, and the boiler, come over here, is going to cause this temperature rise. The boiler is heated and the water changes into high pressure steam. Typically the Rankine cycle is always going to be used with water, changing it to steam and then changing it back into water. The steam is shot out of a nozzle that is aimed at the paddle wheel. The paddle wheel is called a turbine. The turbine produces energy, and the steam coming out of the turbine condenses back into the water through the condenser. You can see temperature coming back down on the graph. That's what the condenser is doing. And this is pumped back into the boiler to start the whole process over again, thus being a cycle. So, we didn't actually do the experiment because stuff went wrong. So here you kind of get a visual image of what I was talking about earlier though, with the boiler. You see the pipes, turbine, you can kind of see the fuel right there in the background. But if you look, when they were making the boiler, it was made out of stainless steel because you have high pressure steam, but apparently when they were manufacturing it, they forgot to coat it, or they forgot to do the right processes to allow the steel to stay stainless. So it rusted and the pressure would not stay constant, which is what you need if you look at the graph. This is how you would have collected your data had we done the experiment. And you can see again that it's actually pretty complex in that you're going to get a voltage, current, different pressures, different temperatures for all of your processes. So you can actually record all your steps for your graph. So we were given data from another group when they took theirs. So here is pressure versus time. And you can see kind of at the 4 stages or 5 stages that you'll get bumps in the right direction for the turbine inlet pressure and the turbine exit pressure. So obviously that the inlet pressure is going to be a lot higher because you're using that to turn your paddle wheel. Same thing goes for temperature versus time. If you look at the turbine inlet tip, it's going to oscillate about 5 times for the 5 steps. And if you look at your boiler temperature, it's going to constantly rise because you're using that fuel to increase your pressure and your temperature. Current versus time is going to oscillate in the same way. This current is used with your turbine, with the energy it creates. Voltage, you can see voltage kind of follows the same oscillation as current, and that's going to be because of how the cycle creates the voltage. Reps per minute, if you look at voltage and look at reps per minute, there's barely any change. This kind of shows you that you're not going to get a whole lot of change in this cycle because it's so well made, that, well, it's supposed to be so well made that it's going to be pretty efficient. Fuel flow is all over the place. And that's mainly because when you're heating up steam, cooling down water, it's going to change density. So you don't really know where it's going to be at a certain time. Here are my steady state calculations. So what this is we basically picked a steady point in time, calculated what our boiler temperature should be, calculate the turbine inlet temperature, exit, boiler pressure, exit pressure, inlet pressure, fuel flow, and then from the initial boiler fill amount of 48 liters, you can calculate how much boiler water you use to calculate your fuel flow and your condensation amount.
Got 5.
Very cool. So what can you do with these calculations? You can calculate the heat flow given by the first law of thermodynamics. This is Q equals m dot Cp delta T. The mass flow rate given by density times area and velocity. The efficiency can be determined by dividing the total work by the total heat transfer. This can be done for any of the steps. You can do the efficiency of the boiler, turbine, condenser, pump, or the system as a whole. So what improvements can we make? We can increase the boiler pressure. An increase in the boiler pressure will result in a higher temperature and for the same temperature, for the same low temperature. And this is kind of confusing, but I'm going to show you in a second on a graph how this makes sense. And this will cause the efficiency to increase because you'll have less work. You can increase pH by adding superheat. So basically what this is going to do is it's going to run the water back through the boiler a second time so that it will superheat again before going into the turbine. Also, third improvement obviously is the design of the boiler so it doesn't rust and we can't do our experiment. Conclusion, you can see that if you, from our original graph, if you reheat it, you're going to get less work done, and therefore you'll have a higher efficiency. Any questions?
So you said it oscillates, like what? So why does that graph oscillate? Like you said it was for each increment or something?
Yeah, like the temperature versus time.
Yeah, so like you said that was like each step or something?
Right, so you look, you have 1, 2, 3, 4, 5, and you look at your chart, you're going to have about 5 different temperatures.
So each step it's kind of like a jump.
Yeah, you're going to see the jumps from the boiler, from the turbine, and the condensation. All right.